So the first question here was pretty simple because for the same reason I told you before that since there's questions based on this, I didn't want students to get this wrong and then to get 4 questions wrong, you know, or 3 questions wrong because they couldn't balance it or something. So this was considered the following unfinished and unbalanced reaction for 11 through 13. We have aqueous lead nitrate reacting with aqueous sodium sulfate, and that's lead 2 nitrate. Nitrate's -1, and there's 2 of them. And one of the products is sodium nitrate. So you have to finish the reaction, and then you have to balance it, basically. Okay. So this is good practice. So I've had decent number of emails and communications with this material. And one of the things we say to do is this is called a double displacement reaction. This is just swap partners. Easy enough to do. We move the nitrate over with the sodium, you get sodium nitrate, right? And you have to be able to know that sodium nitrate is 1 sodium and 1 nitrate, okay? And you know that because sodium's a group 1 metal, which is +1. And nitrate is a polyatomic ion. You can look in your list. Instead of flipping through the book all the time, there's probably certain things that you should have like on pieces of paper in front of you for each exam until you get to the final, of course. Because if you need to look up what nitrate is, polyatomic ion, you don't remember. You don't want to try to remember what page it's on, what table. But nitrate is -1, so you don't worry about the balancing yet. You just got to figure out the products by swapping partners. So you say sodium nitrate, that's just going to be 1 sodium, 1 nitrate. And the other product of swapping partners has to be what? Lead sulfate. That's going to go in the blank, right? And sulfate is 2-. And we already said this is lead 2 here. So we're good there. Okay, and that's the solid precipitate. You look at your solubility guidelines, it'll tell you that, and I can never remember them simply because they're different in every single textbook, but sulfates are pretty much insoluble, and lead is certainly not an exception. The group 1 sulfates will all be soluble. Of course, that's why we saw this is aqueous here. Because all group 1 are soluble, we know that. So that's what this is how a chemical reaction happens. You mix 2 aqueous substances together that are completely soluble and you get a precipitate. That's a chemical reaction, not just a mixture. If that was potassium nitrate, we'd wind up with no reaction, right? Because when you swap partners, you just get a bunch of ions in solution. But here we don't have ions. This is going to be actually sodium plus N nitrate ions, but this is going to stay as a compound, as a precipitate. It's going to form at the bottom of your beaker. Okay, so once we balance it, what are my coefficients going to be? What's the correct answer? B as in boy. We go 1, 1, a 2 for the lead sulfate. Oh no, 1 for lead sulfate. A 2 for the sodium nitrate. Sorry. For the last one, and that gives us the two nitrates, right, that we need, and the 2 sodiums, right? So that's perfect. And of course, the precipitate is easy enough. You've already done that. Oops, wrong one. Fell for my own trap. You have to get the precipitate right. You have to get the formula right. We've already got that. So C is the correct answer. And your net ionic equation is the reaction that's happening. So if you were to do a complete ionic equation, you'd say, okay, aqueous, let's write this as lead 2 plus 2NO3 minus. I'm going to leave out all the aqueous because I just don't feel like writing them. I'm lazy. Plus 2 sodium ions plus sulfate ions, right? Whoa. Plus, yields. Now this stays together because it's a solid. That's my precipitate. You don't break it apart. That's the whole point. plus, and since it's balanced, now I gotta make sure I use the balancing here. So we got to make sure we get 2 sodium plus 2 nitrate. That's your full ionic equation. And I wrote the S for the solid, the rest are all aqueous. And just like math, anything that occurs on both sides of the equation, you can cancel out, basically. So what we're going to do is just look at this, and anything that cancels out, basically, oops, I forgot a 2 out there, didn't I? 2 nitrates, because we have a 2 in front here. Anything that occurs on both sides of the equation are considered spectator ions. If you get a question on exam identifying spectator ions, this is what you're looking for. 2 nitrate, 2 nitrate, 2 sodium, 2 sodium. What's left is your net ionic equation. It also tells you basically if there's a reaction. If you got nothing left, there's no reaction. You could do this with potassium nitrate instead of lead nitrate, and then everything's going to cancel out, right? Because you're not going to have a precipitate forming. So that gives us our net ionic equation. So that would be lead 2 positive plus sulfate. That would be B here. Questions? Okay. All right. Which of the following species would be the most soluble in water? You said that, Abigail? Yes. D as in dog is correct. You go through this, you say to yourself, okay, first of all, I've learned that hydroxides are pretty much insoluble. The exceptions are going to be, as always, group 1 and the ammonium cation. So there's a hydroxide right there. Okay, there's 3 of them. That's just 3 hydroxides because that's iron 3 hydroxide. We know it's not that. And phosphates are also known to be pretty insoluble. And if you look at the exceptions, I think it's just group 1 and ammonia, but it could include like magnesium. I don't think it does for your phosphates, but anyway, it's certainly not barium is not an exception. So that's out. And carbonates are pretty insoluble. Once again, the group 1 and the ammonium are exceptions. There might be one other there, like magnesium carbonate, or, and I always have to remember the trends because they're backwards on some of the species. Or carbonates, I forget if it would be magnesium or if it would be barium or strontium. Anyway, lead carbonate's not going to be an exception. So that's, I'm just thinking out loud, by the way. So that's definitely not the case. And then you get to the chlorides and you say, well, chlorides are all soluble, but there's a few exceptions to that. And one of them is the classic one, silver. So silver chloride's a classic precipitate. And that's one of those ones that halogens that does precipitate. So, and we're asked for what's the most soluble. So calcium chloride, Abigail's right with D. Questions? Okay. Use 15 through 17. Giving you the molar mass of lead sulfate here to save time. And we have a couple questions here on this. If unlimited sodium sulfate is combined with 50 mils of 2.5 molar lead nitrate, what amount of lead sulfate precipitate forms? A minute or so to think about this and see if you can scratch out some ideas and how you might approach this. We did something somewhat similar, I guess, in lecture. You don't even have to write the formula to be able to solve it, but You look at what's happening. Pretty much the same. Is that what we did up here? Yes, the same what we did up here, lead nitrate, sodium sulfate. Yeah, same reaction there, so that's straightforward. How should we do this? Anybody have an idea? Abigail? And you say that solution, you mean the 50 mils of 2.5 molar lead nitrate, right? Okay. So you've got this one solution of 50 mils of 2.5 molar lead nitrate, right? So effectively, we're forming same thing we did up top. That's my precipitate. Same thing we did up top. So effectively, we just need to know how much lead, how much lead is in that solution, because that's going to be how much lead nitrate, that's going to dictate how much lead nitrate you get, right? Doesn't matter how much lead sulfate you'll get. Doesn't matter how much sodium sulfate's there, because we've got unlimited. So just figure out how much lead you have, and the molar relationship between lead and lead sulfate is 1:1. So whatever amount of lead you have, effectively, that's the same molar amount of lead sulfate. You can use the molar mass to figure out the actual mass of lead sulfate. So let's do that. We've got this 50 mils or 0.050 liters times, and we're doing this lead nitrate here, times 2.5 moles per liter. And that'll give us what? 12 point, no, not 12. 1.25 or 0.12? 0.125? 0.125 moles. And this is actually lead nitrate. Whoops. Moles of lead nitrate, which means effectively we have moles of that lead in solution. It's actually 2 plus. We have that much moles of lead in solution. So that's all going to precipitate. So effectively, you don't even need the reaction stoichiometry. You can just say that 0.125 moles of lead 2 positive times, there's 1 mole of lead sulfate for every 1 mole of lead, right? Times, and what's my molar mass? 303 grams per mole. Right? Of lead sulfate. I should say moles of lead sulfate, so it's clear. So now you look at this, you say, okay, well, moles of lead, moles of lead, moles of lead sulfate, moles of lead sulfate. I've got grams of lead sulfate. So you see, you don't really need the balanced reaction. You just need to know the compound, the precipitate. And it works that way because 1 mole of lead nitrate leads to 1 mole of lead sulfate. I mean, it's just, that has to do with the compound's charges and the relationship so that you can just look at the actual product and not worry about the exact stoichiometry. Does that make sense? What do we get for an answer? A, that's what I remember, yeah. So much of these two chapters is this molar relationship. You know, looking at ratios of moles of 1 mole of lead to 1 mole of lead nitrate. You did it with empirical formulas, you do it with all the stoichiometry, it's all this kind of molar relationship stuff. Questions on that one? If you can do that one, you can do the one on the exam. I put one of these on the exam. Questions? We good? The other two are just kind of molarity questions. They're not really stoichiometry. How many grams of lead sulfate are needed to make 100 mils of a 2.5 molar solution? These have to become, if you want to be ready for this exam, these have to become second nature to you. Boom, boom, boom. Molarity. I've got the volume. I've got the molarity. I can get the moles. I can convert the moles to grams using the molar mass. That's what these have to become. So when you're studying molarity, which is going to be hugely important in the future too, treat this like a formula, right? A equals B over C. If you need volume, what do you need to do? Well, you're going to cross, right? You're going to take moles divided by molarity to get volume, right? Yes. Why do I have this based on that? Oh, I see. How many grams of lead sulfate do you need to make 100? Why is this based on that? How many grams of lead sulfate or to make 100 mils of 2.5?
The previous one's 50 mil, and the next one is 100 mil. Just same molarity of the solution too.
Yeah, but you don't even need the. Why do I have this based? This question stands alone. All you need is the molar mass. You don't even need the question 15 to solve this, right? It's just a molarity question. All you need is the molar mass. So you're saying, because this is lead nitrate here, 50 mils. Yeah, I think I did this to base it on this here. But you don't really need question 15 at all. It's just a molarity question. I did it because I gave you the molar mass for all three of these questions. Just realized that's a bit confusing. I'd seen that last year. Yeah, I mean, this is just a molarity question. It has nothing to do with lead nitrate, the precipitate. Yeah. So when you're studying molarity, treat this as an equation, right? That's all it is. If you want to know what the volume is, you're going to take moles divided by molarity, right? You want to know what molarity is, it's moles divided by liters. You want to know what moles are, it's going to be molarity times volume, liters. Okay? So in this case, all we need to do is say 0.1 liters, 3 zeros, I didn't want to lose significant figures, times 2.5 moles per liter, and that's it. Well, no, that's not it. We need the grams, right? Times 303 grams per mole. What do we get? C? C. Yeah, I'm sure I can't see it though, for some reason.
Okay, so in the last question, we solved for lead sulfate precipitate, which
Right.
is what you're solving for
Right.
the second one. And the last one was only 50 milliliters, and this was 100. Literally just multiply 37.9 times 2 and you get.
Oh, I see. Yeah, it just happens to be, yeah. But I set it up that way, 100 mils. Yeah, it's double. And they're both the same molarity too. Oh, yeah. Yeah, I know. Sometimes I do that intentionally. Sometimes I just do it accidentally. So however you solve it, good. If you saw that, that's good. Yeah, I just realized that's right now that she made that. What's your name? Maggie made that clear now. Yeah, it's a 2.5 molar lead nitrate solution. So, and it's 50 mils. So that works too. Okay. So that gives us C, 75.8. Other questions or comments on that? All right. Wow, I messed that spacing up, didn't I? Didn't know where to solve that one. What is the molarity of a 250 ml solution made with 35 grams of lead sulfate? I guess I'll just do it right here. Molarity, 250 ml solution made with 30. I like to just put what I have, mass over the volume, because that's just a concentration of a solution. 35.0 grams. And convert to liters right away. Move the decimal place 3 places. That's all you got to do. 0.250 liters. And what is the molarity? And we need the molar mass, right? And it's still the same problem, right? 17. So it's the 303 grams per mole. And my grams will be canceled out. I'll be equal moles per liter, which is what I want. And what do we get? 35 divided by 2.25 divided by 303. D is in dog. D is in dog. 0.46 capital M for molarity. I think I put like 3 molarity questions on there because I consider this important. 3 different, I might have asked you the volume one case, the mass one case, the moles one case, whatever. It's these pooled questions. So you can get 2 where you're asked to calculate mass or something. It's the only problem with those pooled questions. You get 2, similar ones calculate the same thing, but can't avoid that. Question. All right. If you have 2.5 molar solution of lead sulfate, how many milliliters are needed to make 100 mils of a 1 molar solution? These are the simple plug and chug dilution problems. Okay. And you just got to be able to say, okay, M1V1 equals M2V2, or your book might have used M initial V initial equals M initial V initial. Some people use M concentrated V concentrated equals M dilute V dilute. However you see it in the future, if you take quant, if you're a chem major, bioanalytical, if you're a biochem major, they're all the same. There's different notations, different people. Okay, we've got a 2.5 molar. The only problem I see students make is mix them up. Just keep them straight. That's all. You have a 2.5 molar solution of lead citrate. How many milliliters are needed to make 100 of the 1 mil? Those 2 stay together. So we've got 2.5 molar equals. Oops, I guess I need the V. V initial equals 1 mole and 100 milliliters. Answers are all in milliliters, so I'm not going to bother converting to liters. You don't have to worry about the fact that molarity is moles per liter, because the molarities will cancel out when you bring it over, right? These will ultimately cancel out when you bring this molarity over here and divide. So you don't care that that's in milliliters. And which one do we get? C for 40 mils. Do these quickly so you can spend time on limiting reactant, combustion analysis, empirical formula. Those are the ones that take some time. The stuff in chapter 8 needs to be quicker on the uptake for your calculations. There's no real involved calculations in chapter 8. I guess a precipitate one's a little bit, tricky. One of these, but nothing like doing a combustion analysis, right? Or a limiting reactant or empirical formula. Those are the tougher of the exam. Question. I think you guys are going to nail this one. I have a good feeling. Of course, half the time I don't have a clue. But sometimes I make up an exam. I'm like, oh man, this is way too easy. We're just gonna, I made it too easy. And the average is like 56. And other times I'm like, oh man, I should have gone easy. This is rough. And you guys do 73 average. So half the time I can't figure it out. But I try to stick to the fundamentals and not do anything like, most of the questions are straightforward empirical formula, 2 elements, and I'll tell you about it in a second. All right, so which of the following is not a strong electrolyte? I find that students struggle with this stuff in this material sometimes more than the calculations. The electrolyte stuff, the oxidation reduction, I always get questions after the exam on that. What did I do? I thought this was being, what's going on? That sometimes is the harder part. So let's spend a little time on that. Which of the following is not a strong electrolyte? When you study for an exam, go through each one of these and tell me what it is. What is sodium chloride? Strong electrolyte. It's a salt that's fully soluble in water. Therefore, it's a strong electrolyte. Nitric acid. Oh, I gave it away. What's HNO3? But that's a classic strong one, right? You have to memorize your strong acids: nitric acid, perchloric acid, sulfuric acid. What are the other ones? Your halogens, yeah. Except for HF, hydrobromic acid, iodic acid, not hydrofluoric acid. That is a weak acid. Okay. I think that's all the one that's on your list. Okay. What is CH3COOH? Acetic acid, right? It's an organic acid and it's weak. It's your classic weak acid everybody uses in all Gen Chem textbooks, so recognize it. That's the way we like to write it to make it clear what the acidic hydrogen is. If you see it written another way, it gets confusing, but you'll learn as you take organic a little bit. Sometimes they won't write it that way. What's lithium hydroxide? Strong base, right? It's an ionic compound, but it's also a base because of the hydroxide. And it's strong because it fully dissolves in solution, right? Hydroxides in general are insoluble, but lithium's in group 1. So that's always the exceptions. All the group 1 alkali metals are soluble. There's no exceptions. Oh, that leaves us the last one. Oh, wait. The question was, which is not a strong electrolyte. Okay, see, I caught my own mistake. Last one. Simple salt, right? It's a phosphate, but it's a group 1 again, so very soluble. Question said, not a strong electrolyte, so we have our answer right here. Anything that's not a strong acid, not a strong base, and is not soluble, based on your solubility guidelines, is not going to be a strong electrolyte. But what do we mean when we say strong electrolyte? What are some characteristics of it? Completely associates in solution. What else? It conducts electricity. Thank you. Okay, you good? Which statement about strong bases is false? Strong bases are strong electrolytes. Strong bases are very concentrated. Strong bases are mostly converted to ions when dissolved in water. Strong bases will react with strong acids. All of the above are true. That's correct. So that's your correct answer. Some people want to say E, but no, I can make a strong acid as dilute as I want, right? Just add a bunch of water and you can drink it. It's fine. So concentration has nothing to do with strength. These two are not related. We said the strength is the degree in which it dissociates in solution. Okay? But it can be still really dilute. And I can make a really strong, weak acid that's dangerous. Okay? All right. So how many milliliters of 0.5 molar sulfuric acid are needed to neutralize, bless you, 50 mils of 0.25 molar sodium hydroxide? Now, Talia, is that right? Yes. And I was going to say her name, but she's not here. And I think I forgot it again. I had it the other day. Oh man. Does anybody remember? It's Shakira. That's it. All right. So I think Talia is the one that said in the other class that we can use maybe M1V1. Were you the one that said that? Maybe not. Yeah, that you can do. But remember, for this one, you've got sulfuric acid. So when you look at this, you've got this 2-to-1 relationship here. And if you use use M1V1 equals M2V2, like we just did, you'll get the wrong answer. Because what we have is sulfuric acid plus sodium hydroxide and neutralization reactions. What are my products? Water and salt. Just swap partners, make a water and a salt. A salt then just swapping partners will be sodium sulfate. We need a 2 there because sulfate's -2. And we'll need the 2 here. And we need the 2 waters, right? Is that balanced? Yeah. 4 hydrogens, 4 hydrogens. Yeah, we're good there. So now we're balanced. Now that's 2 in front of the sodium hydroxide. It's going to affect your M1V1. So, but basically it's the same type of approach, right? We got 50 mils of 0.25 molar sodium hydroxide. Keep those together. So here's my sodium hydroxide right here. 0.050 liters times 0.250 moles per liter. That's my M1V1, right? And then if you would ultimately divide, right, by, since we're after how many milliliters, you would divide by that molarity, right? To get your V2, right? But don't forget, you've got to have, this is sodium hydroxide, so we're going to have 2 moles of sodium hydroxide in here for every 1 mole of the sulfuric acid. You got to throw that factor in there. That's the only thing different. And then it's divide by your, since we're after milliliters, you divide by your molarity. Just like you're doing M1V1, you get 1 over 0.500 moles. And you can just do it like this. Whoa. Some people get confused by that 1 floating on the top. So you can just do 1 mole per 1 liter like that. Some students, I get that question all the time. What's the 1? I'm like, well, I'm just dividing by the molarity. So I'm multiplying by the reciprocal. That's the way I do it. That confuses some students. So sometimes if you do 0.500 moles per 1 liter, you're just flipping it. That's all you're doing. Now 1 liter on top sits a little bit better with some people, rather than just having the 1 there. And it is effectively there. It's 0.5 moles per liter in the denominator. So anything 1 over, right, comes to the numerator. And then there's your answer. What do we get? C as in Charlie.
How do you know when to do this versus like the M1V1?
Well, This is a neutralization when you have two different species, an acid and a base. A dilution is taking sulfuric acid and just adding water. This is an actual reaction. You see? So when you read the question, you say to yourself, sulfuric acid is reacting with sodium hydroxide in neutralization reaction. I have to consider the stoichiometry. Now, if this had been HCl, then you can do it just like an M1V1. Because this becomes 1/1, and we don't care about that. I mean, effectively, that's what you're doing, but you can ignore it because it's just 1/1. So you can do it just like an M1V1.
If you write out the equation and the rule ratio of 1:1, it's basically.
You're right, exactly. And when you think about an acid-base reaction, you can think about it like the acid's being diluted in the base, or the base is being diluted in the acid. That's why it works. But just pay attention to your stoichiometry and whether or not you need to throw that factor in. Yes, Mary.
Because is it like what C is like in liters, and so you're wanting it in milliliters.
Oh, thank you. Yeah, very good. So is that correct? Someone else check it? Yeah, okay. I wasn't paying attention. Yeah, so yeah, this is all liters. So we'll get 0.0125 liters. And then therefore we get 12.5 milliliters. Very good. This is why I like to do these in front of a whole class. We catch our own mistakes. We learn from our mistakes. Okay. We good? All right, how we doing on time? Oh, we're good. Doing good. Doing good. All right, now we can spend some time on oxidation reduction because, like I said, it's the last thing, one of the last things we cover, or it is the last thing we cover. And I tend to notice that students struggle with it a little bit. Okay, consider the following reaction. And I tried to keep this basic because you were just introduced to it. You'll come back to this in chapter, I think it's 17 or whatever in Gen Chem 2. It's the very last thing we do in Gen Chem 2. Whole big fat chapter on electrochemistry. It's usually the only chapter on my exam for my last exam in Gen Chem 2. 4 iron, 2 oxide, plus oxygen gas, plus 6 waters gives me 4 iron hydroxide precipitate. Identify which element is oxidized. I asked for the specific element. What's being oxidized here? What's that? Who's saying that? What's it coming from? Abigail? Abigail's right with B, but I can tell that a lot of people aren't too comfortable with that. You only got 3 choices. You got 33% chance of getting it right. So let's start with oxygen. We know oxygen's always what's its oxidation state or charge always? 2 minus, right? Except for the peroxides, which says that you don't have to worry about. So it's 2 minus. That means this is iron 2, right? It's 2 plus. Okay. Now, what's the charge on oxygen here? Oxygen gas. 0. That's elemental oxygen. Don't say -2. It's elemental oxygen, so it's 0. Got to be O2 gas to be 0. And then that's water. That's standard hydrogen and oxygen. So the hydrogen should be +1. The oxygen should be -2, right? And there's 2 of the hydrogens, so that's fine. Now we go to the right there, and that's a hydroxide ion. That's a polyatomic ion that is -1, right? And you know it's -1 because oxygen is 2 minus and hydrogen is 1 plus. So the hydroxide ion is always -1. Right? That's where these polyatomic ion charges are coming from. It's coming from their oxidation numbers. And we did that with sulfate the other day, I think, right? We did sulfate. We said the sulfur 6 plus here because there's 4 oxygens all at -2, right? That's -8. -8 and what gives you -2? +6 for sulfur. That's where these charges are coming from. So that means that iron here must be what on the right? 3 plus. Who said that? Houston is right with 3 plus, right? So now you've identified that iron has gone from 2 plus to 3 plus. What is that? Oxidation or reduction? Oxidation. Reduction is the decrease in the oxidation number. This is increasing from 2 plus to 3 plus. So it's oxidation. Hydrogen hasn't changed, right? It's still +1 on both sides. We recognize that oxygen then, oxygen has gone from 0 to -2. So that's been reduced. Right? And we'll answer the last question too. How many electrons have been transferred? How'd you get 3? Who said 3? You?
Yeah. It's 2 in the oxygen, 1 on the iron.
No, that's not the way you want to look at it. So the iron and oxygen have to equal each other. One's being oxidized, one's being reduced. So the electrons transferred from iron to oxygen have to equal each other. And the easiest way to look at it is there's 4 irons, right? 4 irons, and each one is losing 1, right? So 4 electrons should be transferred. Double check it and say, okay, I've got 2 oxygens, and each one is gaining 2 electrons. So 2 times 2 is 4. So we have basically oxygen has added 2 electrons, and there's 2 of them, right? So that's 4 electrons being transferred. And iron has lost 1 electron, right? And there's 4 of them, right? Everybody see that? Iron's gone from +2 over here. This 2 here means iron. And it's +3 over here. And there's 4 of them. And oxygen's gone from 0 right here, because it's elemental oxygen, to a compound where it's always -2 for our purposes, except for a few exceptions we're not going to worry about. So keep in mind now that oxygen over here, this oxygen hasn't changed. It started at -2 and it's still -2, right? So that confuses people too. Some of the oxygen wasn't reduced, but the oxygen that was in the oxygen gas has all been reduced. The oxygen that was in the water is just now part of the iron hydroxide, and it was -2 and still -2. So just focus on this oxygen right here and realize that you started with 2, so 2 of these over here is all you have that have been reduced. The other 2 are already -2. So don't worry about the fact that you got 4 oxygens on the right. Just look on the left side, I've got 2 oxygens, and they're going from 0 to -2. Because oxygen is one of those ones in so many reactions, right? I mean, so many parts of a reaction that it can be real confusing. If you see nitrate here and sulfate here and oxygen gas here, and it's like, whoa. So, element being oxidized, we decided was iron, reduced oxygen, electrons transferred 4. And we're still not done. What's the oxidizing agent? Let's see, there's a chat question. How is the iron 3 positive now? What do you mean now? It's doing fine. What do you mean by how is the iron 3 positive now? How is it? How is it iron 3 positive now? Is that what you mean? Well, if that's what you mean, we have iron hydroxide. And we just went over here that hydroxide is -1. And there's 3 of them. So that's 3 minus. That means iron has to be balanced, the charge. That means iron's got to be 3 plus. You're welcome. Okay. So what's the oxidizing agent? I can word this another way and you get it right. What's being reduced? It's the same question. Oxygen gas is being reduced. It's the same exact question. The oxidizing agent is what's being reduced, right? It's carrying out the oxidation, right? Stealing the electrons, and that's what reduction is, the gain of electrons. We usually consider the actual compound as an agent rather than a single element. That's why I worded it that way. And I said, well, which element's being reduced. You could say what's being reduced would still be O2 gas. That's fine. But just try to eliminate that confusion and pick the specific element. So that's the oxide. And you can ask, what's the reducing agent? Well, the reducing agent is FeO, right? Because the iron in the FeO is being oxidized, so it's the reducing agent. Okay, so the oxidizing agent is what's reduced. The reducing agent is what's oxidized. Questions? All right. So something I didn't go over, which is in smart work and wind up on your exam, so I guess I should go over it. It's in smart work, it's in the book, so it's fair game, but I didn't leave it out purposely. I just realized, oh wow, I covered this. Okay, so let's say I have a 2.5 molar solution of, I don't know, calcium chloride. Someone tell me what the molarity of the chloride ions is. For R. So imagine I've got a 1 liter solution up here on my bench. Exactly 1 liter, and it's calcium chloride, and it's 2.5 molar. It's pretty concentrated. That's pretty concentrated. You start getting at the whole number of molarities. What's the molarity of the chloride ions? Come on, it's not that hard. Think about it. What? Thank you. It's just 2 times, right? The little 2 down there is the answer. But there's twice as many. There's twice as many chloride ions. So this is going to go into solution, right? And form Ca2 positive and 2 chloride ions. So the molarity of the chloride ions is 5 molar, right? That's all. Just think about what's happening visually. Calcium ions and chloride ions are going into solution. You got 2 chloride ions for every 1 calcium chloride that dissolves. So you have to have double the molarity. So what's the molarity of the calcium ions? 2.5. And what's the total molarity of ions in solution? 7.5. If you ask the total molarity of ions, it's 5 molar chloride and 2.5 molar calcium. So you have 3 ions for every 1 calcium chloride. So it's 3 times 2.5. That's important in things like reverse osmosis when you're trying to take salt water and purify it for drinking water. The number of ions you have is critically important. It's important in all sorts of water treatment for coagulation, flocculation, all that kind of stuff. It's important for cells in terms of osmotic balance and all of that. Cells at high salt concentration will shrivel up, right? We'll learn that in Gen Chem 2. In dilute solutions with not enough ions, they swell. It's all because of the osmotic balance between the cell and the surrounding environment, whether it be blood cells or bacteria cells. All right, questions on molarity of ions? You good? Was that a question? Carbonates. So carbonates are super important. I mention this because they are the buffer in your blood. They're also the buffer in natural waters. So when I say carbonates, I mean things like calcium carbonate, right? That's classic. That's limestone. You live in this area, you should know what limestone is. It's all the gray rock everywhere. Okay, that's why you have no soil around here. I came from New Jersey, where if you put a pick in the ground, that's all you need to do, and you can build a beautiful garden because the soil is deep and rich and thick. And here I dig down 2 inches, I'm hitting rock, and I'm pulling up clay. I'm hauling in bags and trucks and manure and topsoil to get a garden. You guys have very thin soil here, and you have a lot of clay. So calcium carbonate is the main ingredient of limestone. Okay, and when I say carbonates, I mean carbonic acid, right? This is what type of acid is this? Monoprotic, diprotic, triprotic? Di, too, right? It's got 2 hydrogen ions. It's a diprotic acid, just like sulfuric acid. And we saw how important a diprotic acid is when you're doing a calculation up here, right? You had to worry about that here. We changed it now because of the balancing. So what's interesting is, and this is the buffer in your blood, but it's also a buffer in lakes and rivers, is this acts as an acid to form this, right? That's the simple first step. You can also do the second step, right? But guess what? It can also do this and move in these directions because this is not a strong acid. So effectively, this right here is an acid or a base. You see? Depending if this is in your lake or in your blood and a bunch of acid comes into that lake, or you have a acidosis going on, what'll happen is this will pick up the hydrogen ion, form carbonic acid. That's CO2 and water. That's all carbonic acid is. It's a combination of CO2 and water. And you can get rid of excess CO2. So you can neutralize that acid, but it can also, this can neutralize the base and this can neutralize the base by releasing the hydrogen ion and combining with the hydroxide, right? So it acts as an acid or a base. We'll learn about buffers in Gen Chem 2. This is basically what a buffer is. Has the ability to neutralize an acid or a base. And that's critical for your blood because the pH has to be in a very narrow pH range. I always forget what it is. It's like 7.43, something right in there. I just want to point out acid-base characteristics of carbonates. Now, there's a question in the book, and I think it was Mary that asked me this one. And it is, what chapter was that? Well, it's got to be chapter 8. There's an organic acid. I think it was citric acid or something like that. So, and you're asked, what are the, maybe you were asked the product or something like that. Remember that when you asked me? Was it you that, Ilana that asked me, or was it Mary? It was you. Do you remember which one it is?
It was citric acid, I think.
Do you remember what the number is, like 8 point? Yeah, it's chapter 8 though, right? It's got to be 8, obviously. No, it's not this far back. I wanted to point something out when you see. Maybe it wasn't smart work, was it? No. I sworn it was the book. Eight 8.9. 8.8. 8.9. Absolute. Yeah, there you go. Oh, yeah, this part here. Citric acid right here. That's right. So it was this one. The practice part down here, citric acid is a triprotic acid, the molar mass. And was the molarity of citric acid? And so you don't have to, it doesn't even give you the formula, and it tells you a triprotic. You don't really have to know. And, we usually do this in organic chemistry to represent an organic chain. So you don't have to know what it is. And you can just say these 3 hydrogens here represent three triprotic acids, the 3 hydrogen ions that come off. The compound that forms simply is going to be it's just swapping partners. The sodium will bond where the hydrogen was, just like acetic acid, like this. Right? This is what you get. Sorry. All right. So this is just an R, represents an organic compound. We don't care what it is. It's a triprotic acid. Just like with acetic acid, this is the sodium acetate ion that forms, and you're going to get sodium citrate. So the sodiums are simply going to replace the hydrogen ions on the citric acid. You don't really need to know that to do the problem, but it comes up and you're thinking about, how it asks it. It just asks the molarity. And when you do that problem, once again, the only thing you have to worry about is this triprotic. Otherwise, it's just your standard calculation, neutralization we just did. So just like we had the 2 for sulfuric acid, you're going to have the 3 for the citric acid now when you do your calculation. But some people have been confused about what the product formed is. Just put this cation where the hydrogen was, and change the name from citric acid to citrate, sodium citrate. That's all. All right. And the last thing I was going to talk about, where is it? Oh, smart work. So there was a problem on smart work. I think it was Tommy, right? That asked me about it. And what I told you was correct, but it's actually even longer to think about it that way. So it was what was it? It was like a stoichiometry question, and you had 2 reactions. And I can't remember what the reactions were, but there were 2 reactions. We'll just say A plus B going to C, and then it was C plus D going to, E. And the question was something along the lines with relating this one here. It was like calcium fluoride or something like that in the actual smart work question. And it's in chapter 7. And the question was relating these 2. And there was like coefficients in here too. So it was like 2 here, and 2 here, something like that. And the question was something along the lines of like, how many grams of E or how many grams of A you need to form this many grams of E, and it's 2 reactions. We didn't do anything like that in class. But you use the same molar relationship. You say that 1 mole of this gives you 2 moles of that. You use the same thing. It doesn't matter that it's 2 reactions. You see? And I think I told Tommy, like, well, you go from 1 to 2 here, right? And this has to be a 2 over here or something. And then you go 2 to 2 here. So you don't have to worry about that because you'll be multiplying by 2, then dividing by 2. You just look at this relationship here, and that's all you need to do. So just treat it the same way. Mass of A to moles of A, moles of A to moles of B, moles of B to mass of B, and just look at the coefficients of here, and you should be able to get to the correct answer. Many of you have probably done that already, but I'm going to go back and look at it. We didn't do anything like that in class. We had 2 reactions, but it doesn't matter how many reactions you have. Just look at the molar relationship and do your calculations the same way. Okay. All right, let me talk to you about the exam, what came out of it. As always, of course, 25 questions. I do want to tell you one thing, that question that came up in class the other day was, why do you not get copper 1 ions? What was it? It was the what was it? It was copper 2. Was it copper? No, it was copper solid, I think. Copper solid plus silver ions, right? And it gave us copper 2 plus silver solid, right? I think that's what it was. And the question came up, why don't you get copper 1? And I kind of knew the answer because it's the same thing I tell you all the time. It has to do with stability. But the whole reason is I wanted to know a little more specifically. Copper 2 is much more stable in solution than copper 1. You don't need to know this for any sort of exam or anything like that. Copper 2 is much more stable in solution than copper 1. Because you'd say to yourself, we had to have a 2 out here, right? Because the 2 electrons being transferred. So you had to have a 2 here. And you say to yourself, well, why doesn't it just go like this? Copper solid plus silver ions go to copper 1 plus silver solid. You don't even have to worry about balancing it, just be 1 electron. Why doesn't that happen? Because copper 1 ions are not that stable in solution. It has to do with hydration energy, which is beyond us here. But that's why I just wanted to tell you because the question came up. You don't really see much copper 1 in solution at all. All right. Exam now. 25 questions as always. We'll end up only being 9 questions from chapter 7. You have 1 combustion analysis, but there's no oxygen in it. So don't have to worry about subtracting out the oxygen. You know, I kept them simple because otherwise it gets too long. Simple as I can. There's 2 that are molecular empirical formula, kind of qualitative type questions. Not so much math, because you know, you can go from the empirical formula to molecular formula very easily, right? You have the molar mass and knowing that multiplying factor. And then there's 1 empirical formula where you've got to do the calculation. And that's only got 2 elements in it, though. Something like a hydrocarbon, CH, you know, organic compound, the fire, oxygen, something like that. That's 4 questions like this. 1 straightforward empirical calculation, 1 combustion analysis, and then the 2 molecular empirical, more qualitative. There's a percent composition one. And those are the easy ones. You'll do pretty quickly. Here's on this hydrocarbon, what percent carbon is it? Okay. There's 1 limiting reactant problem. I'd like to be more than important, but it's too long. So 1 limiting. And there's 3 straightforward, just like stoichiometric calculations. Hey, you got this much A, unlimited B, how much product do you for? Or if you want this much product, how much A do you need if you got unlimited B, right? That's a question. Kind of like the quiz, only the next step in math. The quiz is like, you know, mole to mole. That's your 9 questions in chapter 7. That leaves us 16 questions for chapter 8. You got 1 on molar ion concentrations, like I just did. You got 3 redox questions. Those are not calculations, just hey, what's the oxidizing agent, how many electrons being transferred, blah, blah, blah. Or what's the oxidation number on this compound? 3 related to precipitation and solubility. These are qualitative questions. Which of these is the most soluble? What's the precipitate that's going to form here? Now here's an equation. Does the precipitate form? What is it? 1 precipitation calculation, like we did today on the review sheet, we did on the slides the other day. How much of this precipitate form? 1 ionic equation. 1 titration, which is just a neutralization, like we just did, sulfuric acid, sodium hydroxide, something like that. 1 acid-base question, that's just a qualitative acid-base question. Identify the acid base in this reaction, or which of these, you know, that's it. 2 electrolyte questions, those are qualitative, obviously. 1 dilution calculation, and 2 molarity calculations.
Did you say was on the test?
How many what?
Oxidation reduction.
Redox is 3. You're welcome. That's all I have. You're free to go.